Right, so what's the formal definition that generalizes these concepts? Assume you have a m vectors from a vector space. We'll say that the set of the m vectors is linearly dependent, which I'm just going to call LD. The vectors themselves are LD. If and only if you can find a non-trivial linear combination of these m vectors that adds up to the zero vector. In other words, you can find m scalars a1 all the way up to am, at least one of which is different from zero. That gives you a linear combination of the m vectors being equal to the zero vector. That's a key concept. That is definitely something you need to know and understand about this course. We'll do plenty of examples. Being 2 vectors being collinear, 3 vectors being collinear. That's an example of vectors being LD, linearly dependent. 3 vectors being coplanar, another example of LD, linear dependence. Linear dependence doesn't just say that there's a solution to the dependence equation, right? This thing here we would call the dependence equation. What it says is that there's a non-trivial solution to the dependence equation. There's a way to write this where at least one of the scalars ai is different from 0. Because, I mentioned it when we talked about collinearity, but it's worth remembering here. There is always at least one solution to the dependence equation. If all of the coefficients, all of the scalars ai is 0, then the linear dependence gives you, left-hand side is equal to 0. 0 times v1 plus 0 times v2 plus 0 times vm is automatically going to give you 0. What you're looking for is whether there is some other solution which isn't trivial. Some other solution where at least one of the coefficients is different from 0. That's a huge difference. If you can find a non-trivial solution, they are linearly dependent. If you cannot find a non-trivial solution, if the only way for the dependence equation to give you 0 is if all of the scalars are 0, then the vectors are linearly independent, Li. Linear dependency as a concept, what it does is it captures some notion of what it means for vectors to be redundant in a sense. Like collinearity means that you don't really need all of them. Any one of them would sort of give you the line, and all the other ones are not really necessary. Well, redundancy implies an objective goal. You don't need, 3 different ways to do the same thing. Here, the goal, the objective is to describe a vector space or a subspace using as few vectors as possible. In that case, if you have a set of vectors that are linearly dependent, some of them are superfluous. You don't need all of them to describe the space of interest. So I gave you the definition of linear independence by saying that vectors are linearly independent if the only solution to the dependence equation is the trivial solution. Let's see if we can actually recognize that this definition is in fact the opposite of that of linear dependence. Like English tells us that they're supposed to mean opposite things. Dependence, independence, these mean different, like opposite notions. Well, let's look at it from the point of view of just 2 vectors. If 2 vectors are not collinear, if they're not parallel, well, amongst other things, if you write the dependence equation, AU plus BV equals 0, the only way this can happen is if A and B are 0. So they're not collinear if and only if the only solution to the dependence equation is the trivial solution. The trivial solution is always a solution, but it's the only one you can have. Then you would say that the vectors are not collinear. For coplanarity, then the dependence equation being equal to 0 if and only if each of the coefficient is 0. Well, that's the coplanarity interpretation of linear independence, right? So formally, if we have a vector space V and m vectors in that vector space, the set of the m vectors is linearly independent, Li, if and only if the only solution to the dependence equation, a1v1 plus a2v2 plus and so on, all the way up to amvm being 0, is the trivial solution, if the coefficients have to be 0. Let's do some examples. How would you show that the set 1, 0, and 0, 1, which consists of vectors in R2, right? This is a subset of R2, not a span, it's just two vectors in a set. How would you show that it's linearly independent? Well, from our interpretation of what it means to be linearly independent, if you're just talking about two vectors, you'd need to show that they're not parallel. They're not collinear. And sure enough, I mean, 1, 0, and 0, 1 as vectors in R2, these are these vectors here. They're orthogonal. Don't make them more non-parallel than this. But formally, what does it mean? It means that if you set up the dependence equation, so you have two vectors here, you'll need two coefficients in the dependence equation, a times the first vector plus b times the second vector, set that equal to the 0 vector, there should only be one solution. If there's only one solution, it's linearly independent. If there's more than one solution, then it's linearly dependent. So what's the dependence equation? Well, it's two equations simultaneously, right? There's the equation in the first components, which gives us a times 1 plus b times 0 equal to 0. Then there's the equation in the second component, a times 0 plus b times 1 equal to 0. Simplify this, that gives you a plus 0, a is equal to 0, and then the other one gives us that b is equal to 0. So that is the only solution. You've solved the system. A is 0, b is 0. That's the trivial solution. That's the solution where both scalars are equal to 0. There's no other solution because any other solution would not give you 0 here for either one of those. And so, yeah, sure enough, these two vectors are linearly independent. What about 1, 1 and 1 minus 1? Again, because there's only two of them, we would expect that we can answer the question by just looking at whether they're parallel or not. They're orthogonal. They're obviously not parallel, but let's use the formal definition. We set up the dependence equation for these two vectors. So a times the first one plus b times the second one is equal to 0. That becomes two simultaneous equations. A plus b equals 0. A minus b equals 0, right? A times 1 plus b times 1 equals 0. A times 1 plus b times minus 1 equals 0. And now we need to solve this system of equations. Well, this is an easy 2 by 2 system. What are we going to do? Let's take the second equation and solve for a. So we get from here that a has to be equal to b, the second one. And if a is equal to b, we plug it back into the first equation. That gives us that b plus b is equal to 0. If b plus b is equal to 0, then we have that 0 is 2b, so that b itself is equal to 0. And if b is equal to 0, from this little bit here, a is equal to 0. So we found a solution. It's unique. It's a solution where a is 0 and b is 0. It's the trivial solution. Because the trivial solution is the unique solution, then these two vectors are linearly independent. Let's look at the third example. We have the vectors 1, 0, 0, 1, and 1, 1. We have more than two vectors, so we're not interested in collinearity here. That's not what linear independence means when you have more than two vectors. When you have three vectors, you're looking at whether these vectors are coplanar or not. Well, they are. They all reside in the same plane in R2, right? If I draw this here, here's 0, 1, here's 1, 0, and here's 1, 1. So they're all in the same plane. And hence they have to be linearly dependent. But let's see what the formal definition tells us. The dependence equation would be a times the first vector plus b times the second vector plus plus c times the third vector should be giving us the 0 vector. We have two equations here. We have in the first part a plus c is equal to 0 and b plus c is equal to 0. Later on, what we're going to see is that this is a system of two equations in three unknowns. The system is homogeneous because the right-hand side is 0. When you have more equations than you have unknowns for homogeneous systems, the solution cannot be unique. And in that case, there are solutions other than the trivial solution. Here's an example of a non-trivial solution. Let a and b both be equal to 1 and c equal to minus 1. In that case, a plus c is 0 because you have 1 minus 1 is 0. B plus c is also 0. And so you have a non-trivial solution here, right? At least one of those is not 0. The set is linearly dependent. Another thing we will see, not something we can use right now because we haven't yet proven this, just as we haven't proved that system of two equations and three unknowns has infinitely many solutions if it is a homogeneous system. But another thing we could look at is say, hey, all of these vectors, 1, 0, 0, 1, 1, 1, they all reside in R2. R2 is a two-dimensional space. If you give me three vectors, there are more of these vectors than the dimension of the space, they automatically must be linearly dependent. But this isn't a trick we can use right now because we haven't proven that this is indeed the case. We haven't even defined the idea of a space's dimension. All right, here's another set. It's a set that contains only one vector, 1, 1, 1. I ask you to show that it is linearly independent. So, all right, well, can't really talk about collinearity and coplanarity here. But it's okay because I have the dependence equation. The formal definition says that I look at a linear combination of this vector. There's only one vector, so linear combinations would look like this. K times 1, 1, 1 plus, well, plus nothing else because there isn't any other vector in the set. So that's the dependence equation. So can we solve this and find a solution other than the trivial solution? The answer is no, right? Because as a system of linear equations, this is three equations. This is the equation k times 1 equals 0 for the first component. For the second component, we also have k times 1 equals 0. And for the third one, we have k times 1 equals 0. The only way this can happen is if k is equal to 0. There's only one solution. It's unique. It's the trivial solution. So the set is linearly independent. Any set that contains only one vector, assuming that the vector in question is not the 0 vector, is automatically linearly independent. Okay, here we're going to do an example where we're not working with vectors in n space, in Rn. The vectors we're working with are going to be matrices. In this case, 2 by 2 matrices. How would we show that these matrices are linearly independent? And here you see the failure of geometry, right? Because I can't really draw matrices as being parallel to one another, or coplanar to one another. But the formal definition still actually applies. What is the dependence relation? I write a linear combination of the vectors in my set. I set them equal to the zero vector, which in this case would be the zero matrix, because all of these vectors are really 2 by 2 matrices. And I show that there's, well, if I want to show that something is linearly independent, I show that there's only one way to solve the dependence equation. If I'm trying to show that they're linearly dependent, I might exhibit a non-trivial solution to the dependence relation. So what's the dependence relation? Dependence equation? It is A1 times the first vector matrix plus A2 times the second vector matrix, A3 times the third vector, A4 times the fourth vector. So I have dependence equation in 4 unknowns. The number of unknowns is always going to be equal to the number of vectors in the set when you're testing for linear dependence or linear independence. 4 variables, 4 unknowns, and what's my system? Well, then once I have set up the dependence equation, I have to simplify it. I have to, do the computations to see what pops up on the left-hand side. So how do I multiply a matrix by a scalar? I multiply each of the entries. So A1 times 1, 0, 0 gives us A1 in this position, 0, 0, 0, plus A2 in this position, everything else is a 0, plus A3 in this position, everything else is a 0, plus A4 in this position, everything else is a 0. And how do I add matrices together? I add them component by component. So I have A1 plus 0 plus 0 plus 0. Then I have 0 plus A2 plus 0 plus 0, and so on. So the dependence equation, its left-hand side, simplifies to the matrix A1, A2, A3, A4. Pretty straightforward. The equation, at least the dependence equation on the right, is going to be the zero vector, in this case 0, 0, 0, 0. And now when is it that these two matrices are exactly the same? Well, I have 4 equations and 4 unknowns. What are the 4 equations? I'm going to take the time to write this explicitly, even though it's sort of silly, because I want you to get into the habit of doing this. The first equation is A1 is equal to 0. So that's one equation. The second equation would be A2 equal to 0. The third equation is A3 equal to 0. The fourth equation, A4 equal to 0. Now in practice, it is unlikely that you're going to get such an easy system to solve here, right? I mean, that system is like so easy to solve, you can read the solution right away. It is going to be that A1 is A2, is A3, is A4, is 0. That's the only solution. In practice, you might have to do something else at that point. The stuff we'll see in the later chapters. We'll have a more complicated system to solve. But because there's only one solution, the trivial solution, then these vectors, which are matrices, are in fact linearly independent. We will see later that the set of 2 by 2 matrices is a set of dimension 4. If there's 4 of them, you're not guaranteed that they're linearly independent. They could be linearly dependent, right? Whereas before, in the previous example, R2 was a two-dimensional space, so if we have more vectors in the set than the dimension of the space from which they come, they're automatically linearly dependent. But if you have the same number of vectors as the dimension, or potentially fewer vectors than the dimension of the space from which these vectors come, then it could be linearly dependent or it could be linearly independent. That is not enough of a test to see if something is linearly dependent or not. One thing though that for sure gives you the answer, when we set up this thing at the end, what we see is that this gives rise to a homogeneous system, meaning that on the right hand side everything is zero, of 4 equations and 4 unknowns. Again, we don't know. It's conceivable that there could be only one solution or potentially more than one. So one solution would be linearly independent, more than one would be linearly dependent. The only thing we can say for certain in these situations is that if you have more unknowns, more variables than you have equations in a homogeneous system, then you will have infinitely many solutions. And so this kind of problem you're trying to solve will tell you that the vectors are linearly dependent. Be wary, be careful about using shortcuts. What about this set here? It has 4 vectors. Is it linearly independent? The previous example had 4 vectors. They were all 2 by 2 matrices, such as is the case here. These ones were linearly independent. Let's see about these 4. So we set up the dependence equation. It would be A times 1, 0, 0, 0 plus B times 0, 0, 0, 1 plus C times 1, 0, 0, minus 1 plus D times 0, 1, 0, 0. That's equal to the 0 vector. That's the dependence equation. This is the thing, the object, whose solution is of interest to us when we're trying to determine if a collection of vectors is Li or Ld. Well, as it happens, it turns out that if A is equal to 1 and B is equal to minus 1 and C is equal to minus 1 and D is equal to 0, then we have 1, 0, 0, 0 minus 0, 0, 0, 1 minus 1, 0, 0, minus 1 plus 0, 0, 1, 0, 0, and that's going to give us, well, what? We have 1 minus 0 minus 1 plus 0. That is indeed 0. 0 minus 0 minus 0 plus 0. 0 times 1 is 0. 0 minus 0 minus 0 plus 0. 0. And finally, 0 minus 1 minus minus 1 plus 1 plus 0 gives us 0. So there is at least one non-trivial solution. So the set is linearly dependent. So yeah, it is easy to show that the dependence equation has a non-trivial solution if I give you the non-trivial solution. But how do we find the non-trivial solution, right? What's the solution to the system? A plus C equals 0. Then we had D equals 0. Then we have nothing for the other one, and then we have B minus C equals 0. That's what the dependence equation reverts to. Here we have a system of 3 equations and 4 unknowns. The unknowns are A, B, C, D. There's only 3 equations. We know, or we will soon see, that there's got to be infinitely many solutions because the system is homogeneous and it has more unknowns than variables. But at this stage, short of trying to find a solution of the system, we don't really have anything else we could do. We have to go and try to find something. Well, it's not super complicated. D is equal to 0, so that's given to us. And then we have A plus C is equal to 0, and b minus c is equal to 0. So we can say, all right, b is equal to c. Great. So we have d is equal to 0, b is equal to c, and the next one is a plus c is equal to 0. Yeah, so we're like this. What can we do here? So I mean, give me an a and a c that added it together give me 0. I guess I could pick a is equal to 0 and c is equal to 0, but then that gives me that b is also equal to c, which is 0. So everything is 0, so that's the trivial solution. But the fact that the trivial solution is a solution is not a bad thing. What we want to show is that it's either the only one or there could be others. Well, this is the key one here, right? If a plus c is equal to 0, you could pick a is equal to 1, so c would have to be equal to minus 1, and since b is equal to c, that's also equal to b, and then d is equal to 0. You don't have a choice. Now, here's your solution. That's the one we had right here. It is non-trivial because at least one of these coefficients is not the 0 coefficient. Now, we were sort of lucky because the system in question wasn't that hard to solve. But some of these systems can be pretty hard to solve. And then what? What do we do? We'll discuss this further. Here's another example of a set that contains 3 vectors. This time the vectors are polynomials. So how do we know if this set of polynomials is linearly independent or if it's linearly dependent? Well, we set up the dependence equation. The dependence equation says a times that first thing plus b times the second thing plus c times the third thing should give me whatever the 0 vector is. Right? Vectors in this case are polynomials. So the 0 vector is a function which is always equal to 0. There's your dependence equation as well. How do you actually see that 2 polynomials are the same? Well, you have to have, I wrote cube here, but this is square, sorry. You have to have that term by term, the coefficients are the same. So the coefficients for the constant terms should be the same. So a should be equal to 0. The coefficients for the linear term should be the same. So b has to be equal to 0. And the coefficients for the quadratic term should be the same. So c has to be equal to 0. That's the only solution. A is equal to b is equal to c is equal to 0. Because there's only one solution to the dependence equation, the 3 polynomials are in fact linearly independent. What about this one here? We have 3 polynomials, 4 plus 4x plus x squared. Then we have 1 plus x and x squared. Are they linearly independent? Linearly independent in P2. So we set up the dependence equation. A times the first plus b times the second plus c times the third. If that's equal to the 0 vector, which is the 0 polynomial, can I find a non-trivial solution or not? So let me write that out. A times 4 plus 4x plus x squared plus b times 1 plus x plus c times x squared. That's the same thing as 4a plus b That's all for the constant term. I'm going to do the linear terms. I have 4a again plus b times x. And finally, I do the quadratic terms of a plus c x squared. What I've done here is I've just rearranged the terms to put all the constant terms together, all of the linear terms together, all the quadratic terms together. When is this equal to the 0 vector? Well, whenever 4a plus b is equal to 0, whenever 4a plus b is also equal to 0. So both of these terms give me the same equation. I won't rewrite it. And the last one is this one here, where a plus c is also equal to 0. So this system has two equations. It has three unknowns, a, b, c. It's a homogeneous system because on the right hand side everything is 0. It is a linear system. I haven't said that, but I'm assuming here things are linear. According to a result we'll see, there's infinitely many solutions, for sure. We can try to find them specifically, right? I mean, a plus c has to be equal to 0. Let's pick a is equal to 1. Then c has to be equal to, well, minus 1. You don't really have a choice here, right? Send the c to the other side. And now we verify what happens with the other one. If a is equal to 1, then 4a plus b is equal to 0. So that's 4 times 1 plus b is equal to 0. So 4 plus b is equal to 0. So b has to be equal to minus 4. So there's at least one solution here that is non-trivial. At least one of these is not equal to 0. You might decide, like, well, why do I need to continue? Like, if I set a is equal to 1, it's not equal to 0, I should be fine. It's like, yeah, sure, you can say that a is equal to 1, but you still need to verify that there's a solution that goes along with that choice of a. Perhaps you say, oh, a is equal to 1, and then if you try to plug it in then you get a contradiction. You get something like 0 is equal to 1, in which case there wasn't a solution when you assumed that a was equal to 1. So you need to make sure you find a full non-trivial solution before you stop the dependence equation stuff. I am not going to do the next example, but I'm going to show you the answer so you can pause the video and sort of make sure you see what's happening. Are the three functions 1 sine at x and cosine at x linearly independent in the space of functions or not? We ask you to show that it is, which means that you need to show that there's only one solution to the dependence equation. Whenever you're done with this one, you can look at the second problem. Is the set 1 sine squared at x and cosine squared at x linearly independent or not? It isn't, because you can find a non-trivial dependence relation thanks to the relationship between sine squared at x and cosine squared at x. You know that the sum of these things is equal to 1, no matter what the x value is, meaning that you can write 1 as a linear combination of sine squared at x and cosine squared at x, and so the three of them together cannot be linearly independent.